The Apollo Moon Missions, Hiding a Hoax in Plain Sight, Part 2 by Randy Walsh.
Project Gemini consisted of 10 manned missions which were regarded as being a step forward in progress in terms of astronaut participation as opposed to just being monitors or passengers of the spacecraft. However, the issue of the manual versus automation would continue even more so when it came to accomplishing the objectives of these missions. The objectives of the Gemini missions were designed specifically to practice maneuvers in LEO for the upcoming Apollo Moon missions. These objectives included long-duration missions, rendezvous and docking, extravehicular activity, and precision landings. It was planned that after the Gemini spacecraft re-entered the atmosphere, it would then deploy a parachute on the last several thousand feet of its descent, and the astronauts would hand-fly their spacecraft with skids deployed to a precision landing on a runway. However, because of the technical and funding issues, it was decided instead to continue with the method of splashdown in the ocean, which was used for all manned missions in the 1960s and 1970s. Lack of funding issues is an overall theme regarding the manned space program. However, a more realistic reason for the claim that there was a lack of funding may have more to do with the realization that Congress knew much more about the impracticality of manned missions to LEO. Further, Congress may have known too of the possibility of manned missions beyond LEO using present technologies. However, NASA still gets an average of about $20 billion per year. Therefore, they could easily prioritize its funding for a manned spacecraft launch capability to LEO if they choose to. As to why they don't, has little or nothing to do with the claim of not being provided adequate funding. One major component of both the Gemini and Apollo missions was that of rendezvous and docking, where the need for automation was made even more apparent. Although NASA claims that Gemini 3 demonstrated manual maneuvers quite successfully, astronaut Jim McDivitt tried unsuccessfully to rendezvous with a spent booster during the Gemini 4 mission. He realized that piloting skills alone were inadequate for rendezvous. In fact, there were those within NASA that would go as far as to question any need for flying skills at all as a requirement for astronauts. Mindell writes, "Afterward, McDivitt attributed the problem to poor lighting, but he was facing something new. Orbital dynamics created a new strange brew of velocity, speed, and range between two objects and called for a new kind of piloting. Catching up to the spacecraft ahead, for example, might actually require flying slower to change orbit. It's a hard thing to learn," observed Deke Slayton, "since it is kind of backwards from anything you know as a pilot." A NASA investigator concluded that training had been inadequate and that the entire program had underestimated the subtlety of the rendezvous task. Gemini 4 taught an important lesson. Pilots could not rendezvous by eye. Note that Deke Slayton was a World War II pilot and aeronautical engineer. He was also a test pilot who was selected as an astronaut for the Mercury program but was disqualified due to a medical problem. He was then made chief of the astronaut office and director of flight crew operations, responsible for NASA crew assignments for both the Gemini and the Apollo missions. By 1972, Slayton had resolved his health problems and returned to flight status. He was one of the astronauts on the Apollo-Soyuz mission. One would assume that NASA was fully aware of these new orbital dynamics and would have known about the problems of using manual techniques for rendezvous before attempting any manned mission. And aside from any claims from some of the Mercury and Gemini astronauts, piloting skills were increasingly becoming less of a prerequisite, while the need for a fully automated and autonomous computer would become necessary. And as we have seen from Mindell's statement, astronauts could not rendezvous manually. The issue of manual versus automation will figure prominently when discussing the lunar landing in a future video. However, with the Gemini program, NASA claimed to have found a way to appease both the astronauts and engineers by adopting more of a hybrid method, having the astronauts participate by interfacing with an onboard computer for many of the programs involved in manned missions. Manual and automation would coexist, for now that is. Or put it another way, astronauts' piloting skills were being seen more of a necessary component that would enhance any success for manned missions, especially when landing on the lunar surface. In essence, NASA needed to build on a heroic fighter pilot image to sell the official narrative to the public, while in turn would solicit the necessary emotional response. This was apparent in the official narrative of the Apollo 11 lunar landing. The unmanned missions. In 1961, NASA implemented a program to use unmanned spacecraft to collect data for the Apollo moon landings. There were 4 different types of spacecrafts designed and built called Ranger, Lunar Orbiter, Surveyor, and Pegasus. The Pegasus missions were designed to record micrometeoroid impacts which would pose a real threat to any of the Apollo missions. However, these missions went no further than low Earth orbit. The Pegasus missions were discussed in Part 1 of this video series. The Ranger Program. The Ranger Program took place between 1961 to 1964. The purpose of these missions was to take the first ever close-up images of the surface of the Moon, then impact the lunar surface after each mission had met their objective. However, there were serious problems encountered with these missions, so NASA did not achieve the overall objective of the program. There were 9 missions in all. Further, Ranger 1 experienced numerous problems after launch. Among them, radio interference prevented ground-based tracking systems from properly tracking the mission. Further, it did not enter an elliptical orbit after the Agena rocket failed to reignite its engine for its mission. Ranger 1 entered Earth's atmosphere several days later. Ranger 2 had similar problems after launch when its Agena rocket engine failed to reignite for its mission, and it too entered Earth's atmosphere several days later. Ranger 3 actually made it out of LEO and was on course to impact the lunar surface until its downlinked ground-based tracking systems failed, causing the vehicle to enter solar orbit, which meant a loss for the mission. Ranger 4 was on its way to impact the lunar surface when it tumbled out of control during separation from its spent stage and impacted the far side of the Moon, therefore it never accomplished its objective. Ranger 5 lost its downlink to ground-based tracking stations, apparently to loss of battery power. It then entered solar orbit, therefore ending the mission. Ranger 6 had managed to successfully impact the lunar surface, but it failed to take any photos, so it too did not meet its objective. Ranger 7, 8, and 9 had met their objectives in sending back photos of the lunar surface before impact, classifying these 3 missions as a success. The images taken by Rangers 7, 8, and 9 enabled the U.S. Geological Survey to make plaster models of the lunar surface for study. This is an important point to remember when discussing the simulation aspect and how NASA used these lunar surface models in simulators, which were a necessary component in faking the Apollo moon missions. The simulators will be discussed a little further on in this series. The Lunar Orbiter Program. There were 5 lunar orbiter missions launched between 1966 and 1967. Lunar Orbiters 1, 2, and 3 photographed potential landing sites for the Apollo missions. Lunar Orbiters 4 and 5 photographed the entire lunar surface. These landing sites were chosen using Earth-based observations, but the lunar orbiters were used to get more detailed photos of the areas selected. Considerations for the landing sites included smoothness of the terrain, number of craters, hills, and cliffs in the surrounding areas, and the amount of propellant needed for the LM ascent for the missions, and a free return trajectory for any of the Apollo missions should it be required due to a failure of the service propulsion system. Note: a free-run trajectory meant that if any of the Apollo missions experienced engine failure on the way to the Moon, they would have been able to coast around the Moon and back to the Earth, in theory that is. However, that was changed after Apollo 11 in favor of a hybrid trajectory supposedly due to NASA's increased confidence in the CSM propulsion system. This meant that the missions would start out on a free-run trajectory and then would perform a mid-course maneuver for more precision in their approach to the landing site, giving up the free-run trajectory. For those who believe the official version of the Apollo missions, one would wonder why this confidence was maintained after the near-alleged disaster of the Apollo 13 mission. Micrometeoroid experiments were done for each of the 5 unmanned spacecraft. Each of them carried 20 detectors to record micrometeor impacts. The spacecraft flew both equatorial and polar orbits around the Moon. Their orbits ranged from approximately 20 to 3,900 miles. Micrometeoroid data was collected for 17 months. The 5 orbiters recorded 22 punctures during a time area exposure of 139 square meters per day. These figures gave an average rate of 0.16 puncture per square meter per day in the near-lunar environment, or about 1/2 of the average rate of flux recorded by the Earth-orbiting satellites Explorer 16 and Explorer 23. The 5 lunar orbiters recorded approximately 22 micrometeoroid impacts per day according to what is documented, and the impacts were greater near the lunar surface. However, there is no mention of any damage to the detectors themselves on the unmanned missions, which leaves one to guess as to how many detectors were actually working during the 17-month period. Hence, the number of micrometeoroid impacts recorded per day has to be considered a conservative estimate, to say the least. Micrometeoroids would have posed a serious risk to any Apollo mission, especially the LM. As documented in Part 1 of this series, the LM walls had a thickness equivalent to 3 layers of kitchen foil, which needs no explanation as to the lack of protection for the astronauts. Either a micrometeoroid impact or an astronaut pulling his foot through one of the LM walls would have ended the mission instantly. And given some of the carelessness of these astronauts while allegedly walking on the lunar surface, causing them to fall over several times and risking tearing their spacesuits, accidentally putting one foot through the LM wall was not out of the realm of possibilities. Radiation experiments were done by each of the lunar orbiters too. Each lunar orbiter had 2 cesium iodine detectors on board. The data obtained from the radiation experiments on board of the 5 lunar orbiter spacecraft had significant implications for the Apollo program. What would be the approximate dose of the radiation experienced by the astronauts in spacesuits, in the lunar module, in the command module? To obtain an answer, the primary investigator, Dr. Trutz Fulsche, analyzed the data recorded by the 2 cesium iodine detectors in each of the 5 orbiters. One of the 2 was shielded by 0.2 gram of aluminum per square centimeter, the other by 2.0 grams of aluminum per square centimeter. Because of the high absorption of the protons and alpha particles per gram per square centimeter in the soft tissue of water, the doses recorded by the lunar orbiter dosimeters had to be multiplied by 2. The analysis showed that all events recorded were of significance to a man in space only where shielding was light, specifically in a spacesuit or in the lunar module. This is a very interesting and revealing quote from NASA, given the lack of shielding for the Apollo missions, especially the LM, which this quote makes very clear. It substantiates researchers' claims that radiation in space would be a hazard to any Apollo manned mission outside of LEO, given the level of protection that they had, or lack thereof. NASA then compared data from Pioneer 5, launched in 1960, to the data from Pioneer 6, launched in 1965, with that of the lunar orbiter. Both Pioneer missions recorded data from solar particle events, and after they reviewed the data from the Pioneer lunar orbiter missions, their conclusion was very revealing and clear. From their data, the inference could be made that in the rare case of a large event group, such as those found in 1959 and 1960, the Apollo astronauts might experience skin doses greater than 1,800 to 5,000 rads in 1 week if no precautions were taken. Doses of 200 to 1,000 rads in a few hours will cause serious illness. Any dose beyond 1,000 means that a quick end to a manned mission outside of the relative protection of Earth's magnetic field. Further, as explained in Part 1 of this series, NASA did not have the capability of recording a true radiation flux, so this data supplied by NASA must be taken with caution. NASA says that the astronauts could experience up to 5,000 rads in 1 week. On average, that's about 700 rads per day. The yearly average dose per person is less than 1 rad. However, given the inconsistencies over the years in the data as reported by scientists directly or indirectly involved with NASA, one thing is for sure. NASA should have a much better understanding of the radiation intensity within both the Van Allen belts and solar particle events. But given NASA and its contractors' propensity for destroying its own data related to the alleged Apollo missions, this data must be looked on with caution. And it seems that NASA has put itself in a very untenable situation, since to reveal the real data for the Van Allen belts and SPEs would surely be akin to admitting that even if Apollo missions reached LEO, they definitely went no further, confirming what many researchers have been saying for many years, that is, the real missions were recorded in a film studio or outside of the crater fields that were blown into the surface at Flagstaff, Arizona. There is a phase in where the Moon is protected by the Earth's magnetic field, which would have given the astronauts some protection in the event of an SPE. But the alleged Apollo missions took place while the Moon was outside of Earth's magnetic field, and the precautions that the Apollo astronauts would have taken beyond LEO should they have encountered a solar storm involving orienting the CSM so that the rear of the spaceship would take the brunt of it. And aside from the obvious intense radiation that would have enveloped the spacecraft regardless of its orientation, no one seemed too concerned about the effect kinetic energy would have had on the highly volatile propellants. As for the LM, no explanation is needed to comprehend the level of protection, or lack of, with the walls equivalent to 3 layers of kitchen foil. Further, a lot of the data collected by the unmanned missions was recorded on magnetic tapes, which are commonly referred to as telemetry tapes. But as we learned in Part 1 of this video series, NASA tends to lose their telemetry tapes. And in fact, the evidence in Part 1 shows that NASA destroyed 14,000 reels of telemetry tapes for Apollo 11. That's an estimated 140,000 reels of telemetry tapes with valuable information that is gone forever, meaning there is nothing to back up any paper records showing the alleged data. There is one more interesting note to make about both the Ranger missions between 1964 and 1965 and the Lunar Orbiter missions between 1966 and 1967. Both of these missions had taken photos of the lunar surface, and more recently, NASA had launched the Lunar Reconnaissance Orbiter LRO in 2009 to map the lunar surface in more detail. And aside from its mission, the LRO also took photos of the alleged Apollo landing sites. However, when comparing the photos from the Ranger and Lunar Orbiter missions to the LRO photos, something is very noticeable about them, and you don't have to be an expert to see it. That will be discussed next. Comparison of photos for Ranger, Lunar Orbiter, and Lunar Reconnaissance Orbiter LRO. We will first take a look at a couple of photos from the Ranger and Lunar Orbiter missions. What is interesting about the photos taken in 1964 to 1965 by the Ranger missions and the photos taken in 1966 to 1967 by the Lunar Orbiter missions is that they are comparable to photos of the alleged Apollo Moon landing sites taken by the LRO mission in 2009. Yet, we see little difference in the quality and resolution of the photos after more than 4 decades when comparing the photos from each mission. However, the LRO photos taken in 2009 of other areas of the lunar surface outside of the alleged Apollo landing sites show remarkable detail which would be expected with 21st century photographic technology. Proponents have gone through great lengths to explain the reasons for the poor quality of the photos of the alleged Apollo landing sites to the superior quality of photos taken of other areas of the lunar surface from the same LRO in 2009, but to no avail since it defies basic common sense. The conclusion is clear. The LRO photos of the alleged Apollo landing sites were photoshopped with as little detail as possible. To show up close detail of the alleged Apollo moon landing sites would require these photos to give a realistic scenario of what the Apollo equipment supposedly left on the lunar surface would look like after decades of bombardment by SPEs, galactic cosmic rays, and micrometeoroids. To estimate the erosion of the equipment left on the lunar surface would be quite difficult to do. So, the obvious way out of this would have been to avoid doing it at all, much like the reasonings for not including the stars in photos allegedly taken from the lunar surface by the Apollo astronauts. Before we leave the subject of lunar photos, there is one more interesting anomaly that I would like to point out. I've noticed that in most of the photos of Earth taken during the Apollo missions, or at least the ones allegedly taken from the lunar surface, the Earth appears to be smaller than it should be. It even appears smaller than the Moon does when viewed from the Earth. This is peculiar since the Earth is almost 4 times the size of the Moon, so it should at least appear larger than that of the Moon when viewed from the Earth, yet it does not. It's quite the opposite. The objective of the Surveyor program was to soft land unmanned spacecraft on the lunar surface, and these were the first American spacecraft to do so. There were 7 missions in all between May 1966 to January 1968 as follows. Surveyor 1 landed on the lunar surface and transmitted 11,237 TV photos. Surveyor 2 crashed into the lunar surface. Surveyor 3 landed on the lunar surface and took some soil samples as well as photo experiments. Surveyor 4 was presumed to have crashed into the lunar surface after its signal was lost 2.5 minutes before landing. Surveyor 5 landed on the lunar surface and took over 19,000 photos and did some soil analysis. Surveyor 6 landed on the lunar surface and performed a liftoff and traveled 2.5 miles before landing again. It transmitted 30,065 TV photos and analyzed soil. Surveyor 7 landed on the lunar surface and took 21,000 TV photos. It analyzed soil and dug a trench. It also took a photo of the Earth. NASA seems to have gained some proficiency in landing unmanned missions on the lunar surface, but as is apparent, not without risks. The Pegasus program. The Pegasus missions went no higher than 500 miles in Earth's orbit. They were designed to record micrometeoroid impacts, which posed a very real threat to any of the Apollo missions. Determining success for the Apollo missions. Researching the pre-Apollo missions reiterated the point about the numerous problems that would have been encountered and the inevitable failures before any success of the unmanned and manned missions were to take place on a consistent basis, specifically for a hostile environment in which scientists knew very little about at that time. This would have been perfectly understandable when designing and engineering new technologies for missions in space, which is why static testing alone with test flights in actual conditions would have been required, especially for manned missions. And although the static testing seemed adequate, Comparable testing standards in actual flight conditions were anything but the norm in certain aspects of NASA's unmanned space program, especially the Saturn V and the LM. We will now make an estimate as to any chance for success with the Apollo missions by analyzing the failures and successes of the pre-Apollo missions. This is purely arbitrary and not what most people would consider scientific, but this can be used as an indicator to estimate the probability of success for any of the Apollo moon missions to have met their objectives. This in turn would help to determine any need to improve on the technologies for these missions. Further, this estimate can be used to improve on many of the aspects of preparing for manned lunar missions, for example, testing of the hardware, software, and training. To be fair as possible, we will give NASA the benefit of the doubt when making this determination. Failures and success of the manned Mercury and Gemini missions. The Mercury missions seem to have met their objectives, so we'll classify these missions as a 100% success rate. Gemini met most of its objectives, but had a clear catastrophic mission with Gemini 8 that nearly killed the crew due to a thruster malfunction and was forced to make an emergency re-entry and splashdown in the Pacific Ocean. So the Gemini 8 missions had to be considered a failure given the potential seriousness of the outcome, especially since there was never a definite answer as to the cause of the thruster malfunction. There was also a launch failure of the Agena target vehicle, which was needed to rendezvous and docking practice with the Gemini spacecraft. The Agena rocket was supposed to have been proven to be relatively reliable, yet one of them failed, unlike the new and most powerful rockets ever launched, the Saturn V, which seemingly had a perfect record, according to NASA. However, since the Gemini 8 mission was considered a failure, that would have given the manned Gemini missions an overall 90% success rate. We already see a hint that the more complex manned missions became, the higher the probability of failure, especially given the minimal testing of these spacecraft. This will be factored into the overall chances of success with the more complex manned Apollo moon missions. Failures and success of the unmanned missions. Although the Ranger program had met some of its objectives, 6 of the 9 missions ended in failure. The Lunar Orbiter program appears to have been an overwhelming success since all 5 of its missions had met their objectives. The Surveyor program had met most of its objectives, however, 2 of the 7 missions ended in failure. The Ranger program led to much more success with the Lunar Orbiter program, but the trend with the Mercury and Gemini programs versus the Lunar Orbiter and Surveyor programs is clear. Since manned missions are more complex, the more likely the chances of encountering problems and/or failures, which factors into the overall success rate of these missions. So far, by combining the manned and unmanned Apollo missions, we see the potential of an overall success rate of 79% for the Apollo missions. A realistic outcome of the Apollo moon missions. As mentioned earlier, for now, we'll exclude the information in Part 1 of this series. Instead, we'll use the failures and successes of the pre-Apollo missions as discussed in this video to determine the probability of success with the Apollo missions. The Apollo 1 tragedy is not included since this occurred during a simulation, and since Apollo 13 had an explosion in one of its oxygen tanks ending in objective of landing on the moon, it is not considered part of the failure rate. Unlike Gemini 8, which made an emergency re-entry into Earth's atmosphere for splashdown into the Pacific Ocean, Apollo 13 apparently continued on and circumnavigated the moon, that is, the objective for the mission changed to getting the astronauts safely back to Earth. And because their trajectory took them around the moon for the slingshot maneuver, better known as a gravity assist, the astronauts didn't seem to be in imminent danger, and as NASA claims, they even managed to take photos of the lunar surface before making it safely back to Earth. Therefore, the new objective for Apollo 13 was met, which qualifies it as a success. Further, there are 3 additional facts that now need to be taken into consideration from the first 2 manned missions to LEO. They are as follows. 1. The Mercury and Gemini manned missions never left LEO. 2. The Mercury missions were nowhere near the endurance of the Apollo mission, and only 2 of the Gemini missions met that endurance. And 3. Further, these manned missions were far less complex in technology than the Apollo missions and didn't involve complex navigation required for circumnavigating the Moon and landing on the lunar surface. To give NASA the benefit of the doubt, we'll deduct only 5% of each of these points from the overall success rate of 79%. This now gives us a 64% probability of success, 79 to 15 for the manned Apollo moon missions based on existing technologies of that era. In addition, we must also factor in the data regarding micrometeoroids and radiation collected from the lunar orbiter missions, showing that cislunar space is a hostile environment. Micrometeoroids and/or radiation could have instantly ended an Apollo mission. But again, giving NASA the benefit of the doubt, we'll deduct only 5% of each of these 2 elements, which now gives a success rate of 54%. Aviation, you say? To put these percentages into perspective, we'll use an analogy. We'll pretend for the moment that the aviation industry had adopted the same flight testing standards as NASA. We'll then use the same percentages in determining the success rate of the Apollo missions and apply it to the aviation industry. We'll leave out the percentages for LEO, duration of unmanned or manned missions, as well as the environmental elements that would have been encountered in LEO and beyond, since we are now talking about the performance of technology in a terrestrial environment. Instead, we'll only use the percentages for the actual performance of this technology used as has been determined in this video series. This, of course, worked out to be an approximation of 79% for the technology used in the unmanned and manned missions combined leading up to the Apollo moon program. There was no further testing of the unmanned and manned missions to try to improve on this percentage. The primary contractors and subcontractors for NASA built more complex spacecraft for the Apollo moon landings without improving on existing technologies for that era, and with very little testing of this new technology in the actual conditions of spaceflight, which was discussed in Part 1 of this video series. So now we will apply a similar approach to aviation and factor in the probability of success for aircraft in general.
The Apollo Moon Missions. Hiding a Hoax in Plain Sight. Part 2 by Randy Walsh.